Okay, so the question I want us to focus on today is this one. What is the derivative of sine of x? You guys are good. Cosine of x. Okay, let's make it a little bit more tricky. What is the second derivative of sine of x? I got you now. It's like, well, the derivative of sine of x is cosine, the derivative of cosine is minus sine of x. Good. One more. What is the half derivative of sine of x?
1 over root 2 sine x.
What? You know? Okay. Maybe you watched some YouTube video and saw this, but how many of you guys have seen this before? 2 people? Good. So most of us will get something out of today's class. What is the half derivative? And it's like what the hell? Like half? Like how am I supposed to do a half a derivative? It's like stop before you get to cosine, right? Like what does this even mean? So this should be your response. Like what does this even mean? But the machinery we built up over the last few days is going to give us a meaningful way to answer this question, right? I mean, the first meaningful answer should just be like, this is not defined. So like, what do you even mean by it? So it's like, okay, so we need to define half derivative. But we should come up with a way of defining half derivative that makes sense, right? Like you could just say it's always 0. Like, okay, that's a dumb definition. But what's a definition that kind of makes sense with these other notions of derivative? And so what I want to do is remind you a little bit of what we built up the last few lectures, and then we're going to use that to answer this question, right? So let's go back to this first problem. The derivative of sine. How can we think of that in terms of linear transformations? Well, we can say the derivative map is itself a kind of linear transformation. I'll call it little d. Well, between what vector spaces? You could have it be between like the set of all differentiable functions, which itself forms a vector space, and then the derivative of those would be like some collection of, the derivative of a differentiable function isn't always differentiable, so it's not necessarily d, but it'll be mapping into something like f, perhaps the set of real value functions. So you could think about the derivative being up here. But the problem is these are infinite dimensional vector spaces, right? And so it's like that's much too big for us to really get a handle on what the derivative is doing. So instead, let's narrow our attention to some smaller vector spaces that will include sine, and I guess should include cosine, right? So that we can meaningfully talk about the derivative. So one such vector space, I'll just call it V. We could define V to just be the span of sine and cosine. Yeah. Where you think about this as some vector space over the reals. Now, you should be like a little bit careful. It's like, is this really a basis for this vector space? We need 2 things for it to be a basis. One is that it should span the vector space, so by definition, it spans it. What's the other thing you want to check? Linearly independent. So you want to make sure there's no solution to like c1 times sine plus c2 times cosine is 0, right? There's no non-trivial solution to that for constant c1 and c2 in the real numbers. But it's like, well, how could you do that? How do you know there's no non-trivial solutions to that? Should I do this over here really fast? c1 times cosine x plus c2 times sine x. This is a bit of review. Like, what are your solutions to this, where your c1 and c2 are real numbers? Well, you want this to be true for all x. So let's pick an interesting x, such as, no, 4 is not an interesting x. 0 is, right? You plug in 0, your cosine is 1. So you get c1, your sine becomes 0, so you just get c1 is 0. And then what's another value of x you might plug in? Pi over 2. Then that recovers for you that your c2 is 0. Right? So sure enough, cosine and sine are linearly independent over the reals. So this is a vector space. What's the dimension of this vector space? 2. So we have a map from a dimension 2 vector space to a dimension 2 vector space. And so what we've been saying is, well, one way to think about linear transformation is instead of thinking up here from going to V, we're going to think about down here going from R2 to R2, where we're going to move from V to R2 by just looking at your coefficient vector. You can move down here by looking at a coefficient vector. But then here, there'll be some matrix, a 2 by 2 matrix, that corresponds, a 2 by 2 matrix, that corresponds to the map D, right? So here, this is just taking, whatever your vector A sine x plus b cosine x is, and sending that down to the vector AB, right? That's your map from V to R2. So what should a 2 by 2 matrix be? Well, the way we cover the matrix D is we just ask, what does the linear transformation do to each of your basis vectors? So like, what does your linear transformation do to sine? And what does your linear transformation do to cosine? So what does D do to sine? Just sine would just be 1, 0. And then what is, okay, so we're asking what does it do to sine? And then we're going to express that in terms of these coordinates. And then we're asking what does D do to cosine? And then we're going to express that in terms of our coordinates. Okay, let's do it. What is D? What is your derivative do to sine? We've already said the derivative of sine is cosine. So what is cosine in coordinates? Yeah, 0, 1. If you just had cosine, that would be 0, 1. So sine gets sent to cosine, which is 0, 1. And what does cosine's derivative? Cosine's derivative is negative sine. So this is negative 1 sine, 0 copies of cosine. So that gets sent to negative 1, 0. So the linear transformation, represented by D, has a corresponding matrix 0, 1, negative 1, 0. Yeah. And as we've talked about before, we can do things like, oh, I don't know, if you want to do a composition. It's like if I want to do a derivative and then another derivative, I can come down here and be like, okay, that's the same as just applying my matrix D twice. So here, we've just seen now that the matrix corresponding to the derivative is just 0, 1, negative 1, 0. And then the matrix corresponding to the derivative squared will just be the square of this matrix, which comes out to be row times column, negative 1, row times column, 0, row times column, 0, row times column, negative 1. Is that where you get? I think so. So like what would d squared do to something like, so there's a little example of this. What would like d squared of, I don't know, sine of x be? That was this example we did right here. It should be negative sine. Well, d squared of sine of x can be represented by this matrix times the vector corresponding to sine of x, 1, 0, which just comes out to be the vector negative 1, 0, which then corresponds to negative sine of x. Okay, I've been a little bit sloppy here. This is the matrix corresponding to this times the vector corresponding to this. This is the vector corresponding to this. But we can carry out the derivative by just doing matrix multiplication. Incidentally, if d squared is negative 1, 0, 0, negative 1, I mean, what do you notice? Like, what is d to the fourth? So this is a nice little observation. What is d to the fourth? What is the fourth derivative? Well, the second derivative squared, right? So we just need to take this guy and square it. It's the first derivative to the fourth, or the second derivative squared. And so, like, what is this matrix times itself? Identity matrix. Which is why when you take the fourth derivative of sine or cosine, you get back to sine or cosine. So are we happy we've seen the correspondence between these matrices and derivatives? We can think about derivatives in terms of matrices. How about the inverse? Do we have an inverse? Is this matrix invertible? Yeah, the determinant of it is just 0 minus negative 1. The determinant's 1, yeah? So we can invert this. So last time we said that the matrix corresponding to the inverse of the linear transformation is just the inverse of the matrix. And one is invertible exactly when the other is invertible. And I don't know, you help me out, I always forget how to do this. I think what I do is I do 1 over the determinant, which is 1. And something switches and something gets switched with sign. How does it work?
You swap the main diagonal and then negate.
So those zeros switch and then these signs change? I think that sounds right. Yeah? Okay. We remember how to do inverses of 2 by 2 matrices, I hope. Sometimes I struggle. Okay, so there we go. There's the inverse. It's like, what does that mean? It's like, what is d inverse of sine of x? Right? It's like, well, you can think about what is the matrix corresponding to d inverse times the vector corresponding to sine of x. The matrix corresponding to d inverse we just said is this guy. The vector corresponding to sine of x is just 1, 0 in terms of our basis, sine, cosine. And so what does this come out to be? Well, this comes out to be negative 1, 0, which is the vector corresponding to what guy? Oh, this is correct. 1 times 0 is 0. Yeah, so this gives you 0, and on bottom you get negative 1. Good, 0, negative 1. And that's the vector corresponding to what? Negative cosine. Wait, what is d inverse secretly? It's the integral. D inverse is the map going the other direction, right? And so if differentiation is going one way, then d inverse is just integration. Well, there's no plus c term at the end, but it's recovering an antiderivative where your constant at the end is 0. So we can think of this now as the matrix corresponding to integration. I think this is really cool, right? Like this is nice. This is really nice. We have derivatives and second derivatives and integration, all with matrices. And maybe now there's some hope for us to answer this question. It's like, well, what do we mean by the half derivative? What is it? Yeah, whatever we mean by half derivative, like to be consistent with the story, it should just be this matrix, the derivative matrix, 0, 1, negative 1, 0, to the 1/2 power. Right? Okay. Let's pause. It's maybe been a few months or semesters, or however long since you've done your first course in linear algebra. How do you figure out what a matrix to a 1/2 power is? Do you remember the trick? It's like, how? We thought that was a hard problem. Now we have this hard problem, right? Like, what is a matrix to the 1/2 power? How do you do that? Anyone remember? How do you raise a matrix to a power? Well, if it's integers, multiply it by itself that many times. If it's negative, you have to do inverse. Anyone remember?
Diagonalization.
Good. So you can do this trick where you remember, okay, you have these things called diagonal matrices. And they just look something like some matrix D where you only have entries on the diagonal and everything else is 0, right? Everything else is 0. And then you're like, oh, with diagonal matrices, it's really easy to raise it to like an nth power. What's a diagonal matrix to an nth power? Where you're like row times column, row times column. All these are zeros besides the stuff on the diagonal. And so it just comes out to be the diagonal entries raised to the nth power. So this just comes out to be your diagonal entries raised to, oh, I shouldn't use n twice. Let me call this m. Let's say it's an m by m matrix. Okay, to the nth power. And then it's like, okay, if that makes sense for integer powers, then like why not just extend the notion to any number n, any real number n, where n is, say some real number. Because we know how to raise a real number to any power, right? If this was like 1/2, you could take the square root of all those values. So if you had a diagonal matrix, this would be very easy. Well, problem is this isn't a diagonal matrix, right? That's okay. One of the big things you learn in your first course in algebra is that if you have a matrix that satisfies some nice properties, which we'll come back and talk about in a second, we call some matrix diagonalizable. If we can write that matrix M as P, D, P inverse, where your D is a diagonal matrix. Diagonal kind of looks like dragonal, and dragons are cool, so that's kind of nice. Okay, so if you can write it like this, where D is your diagonal matrix, and P is some change of basis. So we're not going to go through and fully recover all this. I mean, this is what your first course in algebra is for. But hopefully, as we're saying this, you're like, oh yeah, I kind of remember that, right? And so as you're beginning to remember some of these things, did you happen to remember what a diagonal matrix looks like? What? Yeah, your diagonal matrix here just comes out to be your eigenvalues. Lambda 1, lambda 2, down through lambda m. So I'm assuming here I have an m by m matrix. And what does your p look like? Do you remember? What is it? Yeah, it's your eigenvectors. So P is some collection of vectors that span your eigenspace. It's your eigenvectors. So here we have some, whatever I'll call it, if I use V, you might think I'm talking about some basis. Do you have another? If I call it E, you might think it's elementary vectors. There's no good solution. We're going to stick with V. V1, V2, up through Vm. And so it's like, okay, let's just remind ourselves quickly, what are eigenvectors, what are eigenvalues? Recall these eigenvectors are the guys such that, so your matrix M times V1 gives you like lambda 1 times V1. And it's not just true for one, but it's true for all of them. All of your values from 1 to M. Okay, these are your eigenvalues. But it's like, be careful, because it's like, the moment you have one vector where this is true, you can just scale that vector by 2, and it's still true. Yeah? If I just scale this vector by 2, scaling that side by 2, so the equation still holds. So it's like, oh, once you have one, you have like infinitely many. So we don't want to just say these are like any old eigenvectors. Instead, what we do is we select these to be linearly independent eigenvectors forming your eigenspace. So these are linearly independent eigenvectors. They're the basis for your eigenspace. So maybe we should see an example with this vector, this matrix. Like maybe this is a nice concrete one, and we can see an example for it and see how this works. So we want to solve when is my matrix times V equal to lambda V. So some of this is going to be like kind of reminders of stuff, right? So like, how do you solve this? Well, you can subtract. You get your matrix times V minus lambda V should come out to be the 0 vector. You factor out your V. So we're trying to solve this, right? Okay, so solving this is really saying that V is in, so this is another term you may have forgotten, but this is V is in the null space of M minus lambda times the identity. The null space is the collection of all vectors, so that when you multiply a matrix by that vector, you get 0. So we're just saying V is in that null space. Okay, great. So it's like, okay, when do we have some solution to this? Well, we're going to have a non-trivial solution. I mean, you always have just the 0 vector as a solution. Anything times the 0 vector is 0. But we're going to have some non-trivial solution for V. When? Does anyone remember the condition? I mean, look at this guy. This is a matrix. If the matrix was invertible, what could you do? You can move it to the other side as its inverse, right? But then you'd have some matrix times 0, so you'd have that V is just 0. So if this matrix is invertible, your V is just forced to be 0. That's the only solution. So if you want to have a non-trivial solution to V, you want this to be a non-invertible matrix. So they have a non-trivial solution to V when M minus IL is non-invertible. Which is the same as saying, okay, let's think, I'm invertible when my derivative is non-zero. So to be non-invertible, my derivative must be 0. So this is the same as saying the determinant, sorry, did I say derivative? When I'm invertible when my determinant is non-zero. So I'm non-invertible when my determinant is 0. So we really just want to solve this guy. When is the determinant of this matrix 0? This is how we find our eigenvalues, right? Solving this is going to give us what's called the characteristic polynomial. Right? This is going to come out to be some polynomial in terms of lambda. It's called a characteristic polynomial. And once we have our characteristic polynomial, we can solve then for lambda. And then we get our eigenvalues. And for each eigenvalue, we can ask, well, what kind of vectors correspond to the eigenvalue? and we can recover our eigenbasis, the basis for our eigenspace. Good? So hopefully this is beginning to sound familiar. Let's go ahead and do it. So the matrix we're concerned here with is this guy, 0, -1, 1, 0. So I'm looking to understand what is the determinant of this matrix minus lambda times the density. So I'm going to get some minus lambdas along the diagonal. And these other values are going to stay the same, 1 minus 1. And I'm trying to solve this. Well, the determinant of a 2 by 2 is really easy. It's just lambda times minus lambda times minus lambda. It's just lambda squared. Minus 1 times minus 1 is minus 1. So I get lambda squared plus 1 is 0. Does this look right so far? Have I done everything okay? I think so. Yeah. Yeah. Where do we get M from? I'm just saying in general if you have any matrix M. So I'm trying to, this is going back here, right? I want to solve, like, to have an eigenvector for a matrix, the matrix times that eigenvector is lambda times the vector. So I'm trying to solve this. For us, we're now looking at the example where this is the matrix, right? So I was doing this in general, and now I'm saying let's focus on this specific example where I now want to try and see if I can diagonalize this guy, right? Okay. Solutions to this are plus or minus I, which means that if you try to diagonalize, your guy 0, 1, minus 1, 0, you'll get some guy P times an I, a minus I, and some guy P inverse. Quick sanity check. The determinant of the guy on the left is 0 minus minus 1, it's 1. The determinant here is the determinant of this guy times the determinant of this guy times the determinant of the last. The determinant of P inverse is 1 over the determinant of P, so those determinants will cancel. So the determinant of him should be the same as the determinant of his diagonal matrix. And what's the determinant of the diagonal matrix? 1. So it seems like, okay, at least we haven't done anything too egregiously wrong. How do we figure out P and P inverse? Well, these are going to be the vectors that correspond to, linearly independent vectors that correspond to each lambda. And so to figure those out, let's think about the two cases. The first case is when lambda is I. So we can go back and lambda's I, our matrix up here, our M minus I lambda matrix, is just this matrix minus I times minus 1, 1, minus I. And what we wanted it so that you had some vector that was in the null space of that matrix. That is, you want that matrix times some V to give you 0. We want this times some matrix V, I'll call it the matrix XY, to give you 0. So maybe you kind of remember solving things like this. It's like, well, what constraints does that give you in X and Y? The first guy is saying that negative I copies of X minus a copy of Y is 0. And the second guy is saying X minus I copies of Y is 0. Did I get that right? I think so. Okay. These look like they're very different conditions. But wait, what happens if I multiply this top equation, say, by I? Just going to multiply it all by I. I times negative I is negative I squared, which is negative negative 1, which is positive 1. I times negative 1 is negative I. These equations are actually the same. The second one is just a multiple of I of the first one. But it's the same equation. 0 times I is 0, right? So we actually just have one equation here. The only relationship is that x needs to be whatever y is times I. And so you're like, well, if that's the condition, then your vector v must be something that's in the span of just values, well, y is whatever you want, and x is that thing times I. Are you happy with this so far? Right, like it's the span of that. So y could be 10, and then x should be 10i, but they're all going to be of this form. Great. So that's the case lambda equals I. Now let's look at the case where lambda equals negative I. So we're trying to find what is the null space of the vector. Plug in negative I now. So negative lambda would give you negative I is just I 1 minus 1 times by some vector xy. When does that give you 0, 0? Well, let's look at it. This is saying ix minus y is 0 and x plus iy is 0. Are those really different equations? Are those really independent? Okay, like how do you move from one to the other? Well, down here, just multiply by I and you get the one on top. Right, times an x by an I, you get this. Times the I by I, you get negative 1. Times 0 by I, you go upstairs. So if you get 0, you times that all by I, you should recover the equation on top. So really, there's just one restriction here. Our restriction can be said that whatever y is, it should just be I times x. So whatever this vector is, it has to be something that's in the span of, you help me, what is it? 1i. So there are infinitely many of these guys. There's infinitely many vectors, right, that correspond to, that give you, that correspond to the eigenvalue negative I. You have infinitely many eigenvectors, but only one linearly independent one. And so now what we do is we just make our P a change of basis to just be these vectors. It's just to be these linearly independent vectors. The first, you're going to do the one that corresponds to the first eigenvalue. So since we made I the first eigenvalue, we should make the first vector in P be I1. If we had found that this was the span of 2 or 3 different linearly independent vectors, we would list 2 or 3 different columns, right? But it's just one, so there's just one column corresponding to I. So for the first guy, we just put the vector corresponding to the eigenvector corresponding to I. And then we come and we're like, okay, and the eigenvector corresponding to negative I. And that's our matrix P. Remember this? Kinda? So what's P inverse? Okay, dang it, like I'm definitely gonna screw this up. Those switch and those change sign, right? So I guess it's I minus 1I. And then you multiply by 1 over the determinant. What's the determinant of this? Negative 1 minus 1, so negative 2. So it becomes negative 1/2 of this guy. Okay, cool. So we should have then that this matrix 0, negative 1, 1, 0 is the same thing as P I 1, 1, I times the diagonal I 0, 0 minus I times this other matrix I minus 1, I times by negative 1/2. So I'll just pull that out front. Times by negative 1/2. Now it's like, I really hope this is correct. We may have screwed up. So like, I don't know, somewhere on your paper, like check that this is correct. Because if not, oh my, right? Like I don't know where we screwed up, but we probably screwed up. But as long as we did this correct, then this to any power n will just be, well, I don't know if we said this already. I've written some matrix M as some P, D, P inverse, right? So like, what is M squared going to be? Like, it's the whole thing squared, but what is the whole thing squared? It's P, D, P inverse, P, D, P inverse, right? And so the P inverse and that P cancels. And so you end up with just P, D squared, P inverse. And in general, M to the n is just any of these guys lined up. And so it comes out to just be P, D to the n, P inverse. Because all your P, P inverses cancel in the middle, leaving you just one in the beginning and one at the end. And then what we say is, well, we generalize now to be not just integer values of n, but we say for any value of n. Right, that's the move you do in linear algebra. So here it's like, this to the n is you leave the first and last matrix the same, the change of basis and its inverse matrix the same, and you just raise this middle guy to the n. Which in particular is just going to be him to the 1/2 is just like this guy to the 1/2. Now maybe you forgot like how to do I to the 1/2. Do you remember? What is I to the 1/2? So we're going to use Euler's formula. It's like e to the I theta is, how does it go? Cosine theta plus I sine theta. So if you let your theta be pi over 2, your sine is 1, so you just get I, your cosine vanishes. So I is the same thing as e to the I times pi over 2. So it's like, what is I to the 1/2? Well, it's just this guy to the 1/2. So it's just ei to the pi over 4, which is now just plug in pi over 4 to that guy, which is, oh my, root 2 over 2 plus I root 2 over 2, right? So this middle matrix now has just become, this guy in the middle is just the matrix root 2 over 2 plus I root 2 over 2, 0, 0, root 2 over 2 plus I root 2 over 2. Like that's what it is. So you just need to multiply this out to figure out what this to the 1/2 power is. You can do that.
The bottom right entry is negative I. And the diagonal.
Oh, negative I. Good. So these are both negatives. Great. Thank you. Oh, no, it's negative to the 1/2. So you have to think a little bit like, in order to get negative I, okay. In order for this to be negative I, instead of doing pi over 2, you do 3 pi over 2. So then it becomes 3 pi over 4. And at 3 pi over 4, you're like, I'm right here, where now my x value is negative, so my cosine value is negative. So you have negative root 2 over 2, and the y value is still positive, root 2 over 2i. Unit circle stuff, right? Okay. And so you just multiply that out, and then you'll have what it is. I'm not going to multiply that out. This was a complete waste of time. You need to do this in general, but there's a shortcut. We could have done this all in 30 seconds. By instead, at the very beginning, okay, multiply it out if you want to. But here's like the much more clever way to do it. Our original matrix was this matrix. 0, 1, negative 1, 0. What matrix is that? Like that sends what to what? That sends this vector, the vector 1, 0 to 0, 1, and it sends this vector 0, 1 where? To negative 1, 0. Right? What matrix is this? This is the rotate 90 degrees counterclockwise. And by our uniqueness theorem, we know that there's only one, if you do it to your basis vectors, you do it to everything. So this really is the unique rotation matrix. So like, what is this matrix to the 1/2 power then? Yeah, it's not rotating by 90 degrees, but we're just asking, what is the matrix that rotates by 45 degrees counterclockwise? And so it's like, well, what does that matrix look like? Well, 1, 0 will get sent here. And 0, 1 will get sent here. So where does your 1, 0 get sent? What is this guy? Length 1, it's at 45 degrees. What's the coordinates of that guy? Root 2 over 2 by root 2 over 2, right? And how about this guy? What are his coordinates? Still length 1, but now the x direction is negative, so it's negative root 2 over 2 by root 2 over 2. And sure enough, if you multiply this all out, that's what you should get. So in this case, there was a hack that saved us a lot of time. How does this help us with the original question? What then is the derivative of the half derivative of sine of x? Well, you say this will just correspond to this matrix, root 2 over 2, root 2 over 2, minus root 2 over 2, root 2 over 2, times what vector? 1, 0, which will just give you the vector, root 2 over 2, root 2 over 2, which is, if we express now back in terms of sine and cosine, root 2 over 2 sine of x plus root 2 over 2 cosine of x. This is the vector corresponding to this guy. So that's what the half derivative of sine looks like. Okay. This detour, you might think it was a waste of time. It was important. Because for some other maps, take any other linear transformation. Like the transpose map, right? Like instead of doing the transpose of a matrix, what if you want to do the half transpose of a matrix? Well, you'll have to follow this process, right? Or whatever other linear transformation you want. In general, this is the process you need to follow. But because we had a very nice matrix here, we're able just to shortcut and see, I see what it must be when you raise it to the 1/2 power. But in general, you need to remember how to diagonalize matrices, find your eigenvalues, your eigenbases, all of that to solve this in general. Okay, so we'll stop there.